The International Space Station is a world-class laboratory that is doing a lot of different kinds of science on orbit. Some of it is using the human crew members as test subjects, but some of it is a very different kind of science that's done as well. For example, there is a new experiment that arrived on the Cygnus cargo vehicle last weekend that has a goal of supporting future exploration by looking into the behavior of soils that is found on airless bodies in space. And this morning we're going to learn more about that from Dr. Mark Fries. He is a planetary scientist with the Astromaterials Acquisition and Curation Office here at the Johnson Space Center, and the principal investigator of the experiment known as Strata-1. Tell me, where did the idea for this experiment come from?
Okay. Strata-1 is kind of the outgrowth of a long series of experiments. There's a community of scientists interested in the behavior of regolith. That's kind of like the soil on airless bodies. And there's this community of scientists who are interested in the behavior and properties and characteristics of regolith on these bodies, like, for example, the moon, Mercury, comets, asteroids. And these scientists have been studying the behavior and properties of regolith since the Apollo days. It goes back to then. There have actually been previous experiments to try to understand the behavior of regolith on small bodies. See, we have Apollo samples, we have samples of regolith that were returned by Apollo astronauts. We have a pretty good understanding of the way regolith behaves on the moon, on larger bodies like that, like Moon and Mercury, where you have impacts that throw material up and it comes back down right. But on small bodies, little small asteroids, you have impacts that'll just throw material clean off the body, and a lot of these are what's called rubble piles. They're loosely aggregated collections of material that's kind of free to flow and move as the asteroid orbits the sun. So we don't know a whole lot about the way that regolith behaves on those bodies, and that's the point of experiments like this.
Do we have a reason to believe that it behaves differently than dirt here on Earth?
Yes. Dirt on Earth is composed of the factors that produce dirt on Earth. You have living material. You have a large amount of microbes and dirt and plants and such, or plants and roots and such. There's all the minerals in there have been rounded off usually by some process, weathering, winds, water, that sort of thing. And there's a lot of clays. None of those things are true for regolith. Okay, there's no weathering, there's no flowing water, there's no living microbes. And so what the regolith on these small bodies is composed of is more like impact gardened, fragmented, shocked, shattered pieces of rock, and it behaves very differently than material here on Earth. It's actually fairly difficult to study on Earth for that reason.
So you've decided to study it in the weightless environment. Describe how the experiment operates. What kind of control system do you have so that you can take out the chance factors and really find out how it behaves?
Sure. The point of the Strata-1 experiment is to test our current models of regolith on these bodies and see where the discrepancies lie, if they're there at all. Strata is has 4 tubes filled with regolith simulants on board. And the reason why we have 4 is there's varying degrees of simplicity. We've tried to break out the various factors that go into the behavior of this material and separate them out so we can understand them one at a time. There's the simplest model is just 3 different sizes of glass beads. Okay, it's all spherical, all of them are smooth, all of them are the same material. We go up a step in complexity to the next one, which is 3 sizes of broken glass fragments. So now we've got same material, but angular fragments, something more like you'd actually see in regolith. And then the third one is crushed meteorite. I mean, that's the stuff that the regolith on small bodies is actually composed of. And you have angular fragments of varying density, because this stuff has metal and sulfides and other things in it. And then the fourth is a carbonaceous chondrite to support NASA missions such as the OSIRIS-REx mission, which is going to go collect material from the regolith of a small carbon-rich body.
And do you just let it be and see how it reacts when there's no gravity to work on it, or are you doing something else to it?
it turns out the vibration environment on the International Space Station is fairly similar to what we'd expect to see on these small bodies. You have the occasional thump, and a kind of a low-level background of movement. Previous experiments by University of Central Florida on short-lived parabolic flight, short-duration parabolic flight experiments have shown that we need to do these types of experiments over spans of months and years to really understand the behavior of this material. So what's going to happen is each of these tubes the material has been sorted and it's held in place by a device we call the entrapulator. And when the instrument is activated here shortly, within next days or weeks, the entrapulator will retract and allow the material to flow free. And it's just going to be exposed to the ambient vibration environment on ISS, which will be carefully monitored with the SAMS instrument package, which is bolted to the front of Strata 1 right now. So we get the vibration data, and we will watch the behavior of each of these materials. There's a camera for each tube, and we're going to take pictures at a regular cadence, and we'll have time-lapse imagery basically over the course of a year to watch how this stuff sorts and and rearranges itself under this vibration environment in microgravity. And then it comes back to Earth. We re-engage the entrapulator, so nothing moves again. Bring it back to Earth, and we will core these things out carefully and look at the distribution of particles in terms of size and density where appropriate, and compare the results to the existing models.
Very interesting. Now, this experiment is the product of a program here at the Johnson Space Center that was designed to get experiments to flight faster than what has been the norm in the past. How did that work out for you in getting Strata 1 to fly?
Yes, it's called the 1E program. Historically, getting experiments to the space station has been a multi-year experience. Strata 1, there was Strata 1 and several other 1E Pathfinder experiments, and we got Strata 1 from concept to delivered hardware in 10 months. So we took all the scheduling, everything that had been set up for these longer duration development procedures and condensed it to 10 months. It shook the system pretty well, but it didn't break. If it did, then Strata wouldn't be on ISS right now. We had a lot of good people helping who put in time after hours, time on holidays, and got this thing done. Had some good lessons learned of how to make this work seamlessly for future 1E experiments, and I hope to see more 1E experiments as we go forward.
We're looking forward to see how Strata shakes out over the year too.